without further ado, why don't we just jump into our first talk? Uh, we have an amazing keynote speaker, one of the fathers of DevOps movement, Dave Farley.
Welcome to my talk. I want to talk today about scaling up software development and the challenges that we face when we try to do that. Most organizations at some point, if they're successful at all, are looking to try and be able to deliver software more efficiently, and so start thinking about scaling up. But it's a difficult problem in software. And I think that the best way in which we can kind of think about that and start to address it is to apply some engineering thinking. And that's really the theme of my talk today. So one of the places to start really is to start thinking about what our problem really is. And I think often when we start thinking about the creation of things, we think in these kinds of terms, and we worry about the sorts of things that we can't afford to get wrong in order to solve the problems that are in front of us. But this is not our problem. In software development, this is not a problem that we ever face. Our problem is much more like this. Software development has some interesting and pretty much unique properties. We are going to generate, the product of our work is a stream of bytes. We're going to generate some code. We're going to create a stream of bytes. And once we have that stream of bytes, however big and complicated the system that stream of bytes represents, we can just reproduce that. At the push of a button, in effect, we can just clone that as many times as we like. That is deeply unusual compared to other forms of human activities. We can create entire systems, however large, essentially for free. We don't have production costs. Ours is not a production scaling problem. This is not the part of the problem that we need to solve. And so we tend to the conventional thinking that we apply, brought in from other industries, doesn't really apply. We don't scale in that way. This means that applying ideas like production line thinking is wrong. Just creating cookie cutter solutions is not going to work. It's not reproducible. Standardized approaches are not applicable because every time we are solving a problem, that problem is unique or unusual. Otherwise, we'd just be pushing the button and cloning what we had before. So we are always doing something else. Software development is an exercise in learning and discovery, not in production engineering. So we need to optimize to be fantastically good at learning and discovery. What that means is that we need to take ideas like iteration seriously. If we want to be able to learn, we need to divide up our work so that we can reflect on what it is that we've done. And that means that we need to work in a series of small steps and inspect those steps. It means that we need to take ideas like feedback seriously. We've got to gather information and bring that back so that we can reason about what it is that we've done and what we've learned from it and how we can make progress further. We need to make progress incrementally so that we can move forwards on a variety of different fronts and grow a system piece by piece as we learn more about what's going to work for our users and our customers. We need to be experimental. We are never going to get things right first time. So we should work in a way that allows us to try ideas out and select the good ideas to move forwards with, and hopefully identify the bad ideas so that we can discard them and not waste time, money, and effort on them. And we need to be empirical. We need to be learning from the real world and not our imaginary version of it. We need to catch data. We need to gather feedback from production and understand how our ideas, our products, our software land with our users, and use that information to refine and improve our products over time. Software development is also deeply about managing complexity. If we want to be able to scale up, then we've got to be able to somehow shield ourselves from the innate complexity that is in software. This is a big deal. So we need to figure out how to optimize to manage this complexity. And for that, we need some probably familiar but pretty fundamental ideas that should be at the heart of our thinking when creating software, and particularly when trying to scale up its production. We need to think in terms of modularity. We need to build components of systems that are in some way isolated from one another. Abstraction. We need to draw lines at the boundaries of our within our system, so that one part of the system can evolve more independently of another. We need to think about ideas like separation of concerns that allow us to achieve some of this abstraction and modularity. Separation of concerns is a tool that allows us to separate out different parts of the software that are responsible for different parts of the solution. We need to prefer loose coupling. It would probably be slightly more accurate to say try and identify appropriate levels of coupling depending on where we are working, so that software that is closely related can be close together, therefore cohesive, and software that is less closely related can be further apart, therefore loosely coupled. And this enhances the separation of concerns, the abstraction, and the modularity. All of these ideas are fundamentally about managing the complexity in software and, to be fair, in the organizations that create it. Information is a slippery idea. These ideas are just as true of the organizations that build the software as the software itself. A software development organization is an information system in its own right in some ways. So ideas like concurrency and coupling that cause problems in software are absolutely fundamental to causing problems in organizations too. And so we need to think about those in the way in which we structure and organize ourselves in order to be able to deliver good software at scale. So what do we need to do to be able to do this? We need to first recognize that software development is a creative discipline. Dependencies to minimize them. And we need to apply creative engineering thinking to the development of software and our organizations in order to be able to deliver the software that we are trying to develop. Here are some principles that I think are important to get some of these things right. We need to optimize for learning, as I've already discussed, and also optimize to manage or limit the complexity of the systems that we are creating so that they fit into a human head. The pieces that we are working on are understandable, comprehensible. We need to be able to control the variables. And this too goes to compartmentalization, but also much further. We need to think more scientifically and close down the scope of our evaluations so that we understand the signals that we get back from our evaluations, our tests, our trials, whatever they may be. We want to make evidence-based decisions. We want to run consciously a series of experiments and figure out what it is that we hope to learn from this experiment and what data we are going to collect and how we are going to understand that data. And we control the variables so that we can make sure that the signal that we get back from those experiments is clear. I think another of these kinds of lessons that we can kind of take from science and true engineering in other disciplines is to start off being fairly humble about where we are in our understanding. A good starting point is to assume that we've never got the right answer. Assume that all of our ideas are wrong and then find out ways to prove that they are wrong through more experiments. That's a much healthier way of making progress than to start off thinking that our ideas are great and are perfect and are always going to work. It's much healthier to assume that we might make mistakes and work in ways that will allow us to correct them if we do. There are a couple of important tools that I've come to value significantly over the years, and these are the ideas of testability and deployability, and these play significantly into this more scientifically rational engineering approach that I am describing here. Let's start off with testability and think a little bit about what that means and its impact. So what do we value in good software? What are the attributes of good software? I think the first is kind of obvious. It has to work. But then it should be modular, as we've discussed, loosely coupled, high cohesion, good separation of concerns, exhibiting information hiding or abstraction. These are all ideas that I've just mentioned in terms of managing the compartmentalization of our systems. But I think these are properties that, if you think, they've been true for the whole of my career in terms of what people value in software. Whatever the nature of the software, whatever it did, however it was created, if one piece of software has these properties, it's modular, loosely coupled, highly cohesive, good separation of concerns with information hiding, it's going to be better than software that doesn't. So these are in some ways concrete representations of value. So what do each of these things mean in this sense? So modular code is code which is separated into independent modules. I'm not going to read all of this stuff out, but it decomposes the problem into simpler chunks. And solutions are then more independent as a result, because each of those chunks is hiding some information from some of the other chunks. Solutions are more composable as a result of this chunking up of the solution, and solutions are also more scalable. We can clone each of those chunks and allocate cases to many different versions of them and scale out horizontally in that kind of approach. Loosely coupled. Loose coupling is an approach to interconnecting of components in a system so that those components depend to each other to the least extent practicable. We're trying to ensure that our components are capable of being developed and evolved more independently of other components. Therefore, we're going to tend to prefer loose. There are times where we want tighter coupling, we want more cohesion within a service, within a piece of code, a module of code. We want the code to be cohesive and probably fairly tightly coupled. But on the whole, as a broad strategy, preferring loose coupling is going to allow us to scale more effectively. We can think of these things kind of slightly more colloquially. My favorite description of what good design means comes from Kent Beck, which is moving stuff that's related closer together and stuff that's unrelated further apart. That's really what we're talking about when we're talking about coupling and cohesion. So loose coupling tends to reduce the risk of change in one place affecting another. It helps to isolate the problems and helps us build more modular systems and allows us to decompose bigger problems and work on them in parallel with other teams in a more modular way. Cohesion is kind of the flip side of loose coupling, I suppose, in that it's about making sure that the modules are, the contents of a module are closely related to one another. The degree to which elements of a module belong together is the official definition. So this allows us to focus on reducing the module complexity so that it's doing one thing and doing it well. That improves the maintainability of our code bases and gives us more opportunities, again, for reuse. Separation of concerns is a design principle for separating a computer program into distinct sections, each one focused on doing something, one part of the problem well. The classic description of separation of concerns is one class, one thing, one method, one thing. Again, this tends to simplify development. If we are clearly working on the thing in front of us as we are writing code, if that's focused on doing one job and doing that well, it's easier to think about testing it. It's easier to understand what's going wrong. There are fewer places for mistakes to hide, and a mistake in one part of the code is less likely to propagate to others as a result. This helps reduce the coupling and improve modularity and the cohesion of our software when we're doing these kinds of things. And information hiding or abstraction. It's a powerful programming technique because it reduces complexity. One of the chief mechanisms of information hiding is encapsulation. I think information hiding often, for the wrong reasons, gets tied up with the ideas of object orientation. Information is not only a function of object orientation. Information hiding is about this modularity thing. We want the concepts in our code to be distinct from one another. We want the concerns to be separate, and therefore we need lines, seams of abstraction within the designs of our code that kind of build a little wall between one part of the code and another. Again, reduces coupling, improves cohesion, aids modularity and separation of concerns, and so on. So what drives quality into software? Well, before test-driven development, it was only down to the skill, experience, integrity of an individual programmer. That was it. That's how you got quality code. Test-driven development is something else. Test-driven development is, I think of it as an engineering discipline in the sense of allowing us to engineering a solution and getting a higher quality result. Test-driven development is most simply described as 3 words: red, green, refactor. And the idea of this is that we're going to divide our work up into these 3 little phases, these 3 steps, all of the time. We're going to start off by writing a test, running it, and seeing it fail. We're going to write the absolute bare minimum of code, just enough to make the test compile and no more. If you're using a compiled language. And then we're going to run the test, and we want to see it fail. And we want to see it fail in a predictable way. We want to predict how it's going to fail by, I generally speak the error message that I expect to see at this point when I run a test. Next, we're now in an unstable position. We have a failing test. Our build is currently broken if we were to commit this change. And so we want to make changes to get back to a stable point. So we're going to write the code to make the test pass. And we're going to do that as quickly as we can to get back to this stable point before we start doing things that are too clever. And then we're going to do the clever things, which are modify the code to make it clean, elegant, beautiful. And that's the refactoring step. So red, write a test, see it fail. Green, write enough code to make it pass and run the test again and see it green. And then while it's stable, we're going to refactor the code and make it beautiful and elegant to make it easy to read, easy to understand, nicely factored, all of those good things. And then we move on and do that again. So what are the properties of code that allow us to run these kinds of tests, to make the code testable? Well, it has to work because the test has to pass. The test is asserting something, and so it has to work. It's going to be modular because we're going to focus on testing a particular aspect of that piece of code, and that's done most easily if we can just focus on testing within the bounds of a particular module. It's going to be loosely coupled. We'd like it to kind of, not be bringing in lots and lots of dependencies and relying on chatting to lots of other bits of code, because we'd like to control the variables in a way that we can focus to get the answers that we want out of it. It's going to be cohesive, though, because when we ask it to do something, it's going to do that thing and give us an answer, again, without necessarily collaborating with lots and lots of different unnecessary other parts of the system. And it's going to have a good separation of concerns because we want to be able to have our tests standing outside of the code and describing the behavior of the code from the perspective of a consumer of the code. By now, these should be looking pretty familiar to you. And we're going to exhibit information hiding. We want the test to be testing the behavior of the code, not how the code works. So what does this mean? Well, before we had the skill, experience, integrity of a programmer that would impact on the quality of our systems. But now we also have test-driven development, which amplifies those same properties. The properties, the qualities of, the attributes of high quality software are the same in both of these cases. This doesn't eliminate the need for skill. It's not going to make bad programmers great, but it will make bad programmers better and great programmers greater. So this is kind of a talent amplifier. Test-driven development does what engineering in other fields does. It allows us to improve the talent of a software developer and get a higher quality outcome, whatever level they are at. Let's look at this in just a more practical sense and just work through a little more of an example. So here's a class that I've written. It's a class that represents a car, and this car has a petrol engine. So let's think about testing this petrol engine. So there's a method here called start, and when we're going to start the car, we're going to put the car into neutral, we're going to apply the brakes, and then we're going to start the engine. So what's the test that we could write? So we're going to write a test, should start car engine, and we're going to create our new car. And then we're going to say start on the car, and that's all we can do. There's nothing that we can assert that's going to tell us whether it worked or not. So this code is not testable. So let's modify this code a bit to make it a bit more testable and see whether we can do better. So here's a slightly better car. So now I've made a change, and the change is this change. Instead of creating a petrol engine as part of the car, I'm passing an engine into the car. What that allows me to do is to cheat in my test. So here's my test, should start a better car engine. So here's my fake engine. Ooh, what's a fake engine? Here's an example of a fake engine. So I'm going to implement the same interface as a regular engine. And in this case, all I am doing is I'm just checking that the start method on my fake engine was actually called. In reality, if I was doing this in a real code base, I'd probably use a mocking framework to do this work for me rather than write it myself. But this is all I'm interested in. Does it actually call start? So now I'm going to create a better car. I'm going to pass my fake engine in. As far as the better car is concerned, it doesn't know it's a fake, but hey. Now we're going to call start on the car, and now we can assert, did the engine start successfully? Now our code is testable. So here's my class again. In my better car, model code somewhere, I wanted to create some cars. So I could create a better car with a petrol engine. But without changing any code, I could also create a better car with an electric engine, or a better car if I was some kind of crazy person with a jet engine. I am not constrained. So I hope you will see that just following the simple track of testability by improving the car class to make it more testable, I have now got more flexible code. Even if I throw the test away, this design is better than the previous design because it's more flexible. I can use it in more context. It's less likely to be buggy because I've not compounded the bugs that might be in a petrol engine with the bugs that might be in my car. The bugs in my car are one thing. The bugs in the petrol engine are now a different, separate set of problems. And so this is a better design. The other tool that we can use to think about and improve the scalability of our development approach is to think about the deployability of the software that we are creating. This is a picture of a thing called a deployment pipeline. This is at the heart of continuous delivery thinking. Continuous delivery is about working so that our software is always in a releasable state. And the deployment pipeline is a tool, a mechanism to allow us to achieve that. The objective of a deployment pipeline is to go from a commit of some kind to a releasable outcome. The whole point of a deployment pipeline is to go from commit to releasable outcome. So if you've got a deployment pipeline that just does the build or just does the test or just does the deployment into production, it's not a deployment pipeline. A deployment pipeline goes from commit to releasable. Now that starts to say something important. If this is releasable, that means there's no more work to do. There's nothing else to do to decide whether we can push this into production or not. It's releasable. That means that all of the evaluations that we need to take place before we have confidence to make this release into production take place within the scope of the deployment pipeline. So no more testing to be done at the conclusion of a deployment pipeline. No sign-offs, no integration tests with other components of the system. If the deployment pipeline says it's good to go. It's good to go into production. That's the objective. That's what we're trying to achieve. For that, we have to take these ideas that I've already discussed really seriously. The scope of a deployment pipeline needs to be a module, in some sense, a whole system, a part of a system that we can evaluate completely. These are the principal tools that allow us to scale software development and to divide the problem up into pieces that are deployable and evaluatable to a deployable conclusion is kind of the key step in achieving this. So what does this mean in terms of scaling up? What does scaling really mean? We can scale the size and complexity of the systems that we create for sure, and we can scale the size of the organizations to create things more quickly. The second one doesn't work alongside the first one. You can do either one of these things, but not both at the same time. You don't grow a massive scale organization by just adding more and more people and more complexity. So you kind of choose which one of these things you're going to do to some extent. The problem here is kind of classically related by Fred Brooks' quote in the Mythical Man Month written in the 1970s, which is that you can't make a baby in a month with 9 women. There are some limits to how far you can scale particular problems. Parallelism is a wonderful thing when it's applicable, but as soon as you need to bring information back together again, parallelism comes at often an enormous cost. Small teams are really important. In a study of team size, a study of more than 4,000 completed projects, they divided the cohorts up into teams of 5 and fewer people and teams of 20 and more. And then they did kind of meta-analysis just on the code bases of these teams. And they measured how long it took to go from 0 to 100,000 lines of code for each team. On average, it takes a team 9 months to go from no code to 100,000 lines of code. And as you probably would predict, the teams of 20 people got there sooner than the teams of 5 people. But over a period of 9 months, they got there sooner by a week. They were 1 week quicker to create 100,000 lines of code than a team of 5 people. That means that person for person, a team of 5 people is nearly 4 times as productive as a team of 20 people. And then you start to look at the quality of what they created. The teams of 20 people and larger created 5 times as many defects as the teams of 5 people and fewer. So if you want to move forwards with high quality as efficiently as you can, you must have small teams. The more people you add, the slower you're going to go. And this has been known for a very long time. I already quoted Fred Brooks' book from 1970, which was saying much the same kind of thing. So if we want to think about organizational scaling, there's some kind of really interesting stuff here that's worth considering. There's some fascinating research from the Santa Fe Institute for nonlinear dynamics, and they talk about these things called space filling networks. So these are, how do you organize information groups to fill a space? And the classic way, you can think of this as kind of organizational scaling. What's the structure of your organization? And the classic traditional way for creating large organizations is to organize them hierarchically like this. You build some kind of tree structure in which there's kind of reporting that goes up the chain, and the most important decisions are made at the top of the chain and the less important decisions are made lower down. At least that's what you think is going on. And these kinds of structures mathematically have some really kind of interesting properties. If you look at this traditional structure, there's this number that keeps cropping up, this 0.85 or 85%. And it just crops up over and over again. For example, if you want to double the size of a traditionally structured business, how much does the productivity go up? 85%. It doesn't go up double. So there's kind of a law of diminishing returns. The bigger the organization goes, the less and less and less improvement in productivity you get. However, there's also the other flip side of that, the economy as a scale. If you double the size of an organization, how much extra infrastructure do you need? How many more desks? How many more computers? How many more servers? Heating supplies, canteens, whatever it is, also goes up by 85%. There's another kind of space filling network, kind of small local costs. Sorry, small local networks. This is kind of the social the social network idea. You've got little clusters who are loosely related to one another. Little clusters that are closely related within the cluster, but loosely related to other parts of the organization. This has some really different scaling properties. The number that keeps cropping up for structures that look like this is 1.15. This is much more unusual as an organizational strategy, but does exist, and it exists in one particular place rather famously. This is how Amazon organize themselves. If Amazon doubles in size, it more than doubles in productivity. That's interesting. That's really fascinating. That's really deeply unusual. Economists have known about the 85% scaling rule for a very long time. Amazon kind of turned this on its head and changed the game. Every time they double in size, and they've doubled in size quite a lot over the last few years, they more than double in profitability, productivity, all of those sorts of things. Interestingly, they also more than double in the costs. They also have to invest more in the infrastructure to support these separate teams that they're more costly. So these economies or costs of scale change in unexpected ways. The infrastructures increase by 115%, but productivity, revenue increases by 115%. So if you want to scale your organization, this more distributed model is the much more scalable approach. And there's good maths behind that. And as I say, Amazon are deeply unusual in this, but nevertheless, this is stuff that they knew about and they consciously did. Jeff Bezos was an investor in the Santa Fe Institute that came up with this maths. To scale up problem solving needs to be distributed. The more you try and kind of create those hierarchical structures, the more you're going to slow down problem solving. So what you want to do is that you want to devolve problem solving to the edges of your network, to the people doing the actual work. What this means is that you want small autonomous teams. You want the teams to be able to make their own decisions. To a large degree, there's some great research from the State of DevOps report that says things like one of the key predictors for high quality and high productivity in a team is the ability of that team to make decisions without coordinating their decision making with anybody outside of the team. That's kind of interesting. What does that mean, though, in terms of what does leadership or management mean for these kinds of teams? Well, we want the teams to be working so that they're gathering their own feedback, they're making their own design choices, they're deploying their own software and understanding what that software means to their customers and their users, all of that kind of stuff. We want them to be autonomous. But that doesn't mean that there's no room for kind of leadership or steering what people need to do. In this case, though, leadership is really about the strategy, you know, it's the big goals, the vision. So let's do this amazing thing. We don't know how to do it. You're the smart people in the teams. You figure out how to do it. Give them the task to solve, rather than the means of solving it, the rules of how to solve it, and then describing the boundary parameters. Do whatever you like, but here are the constraints that allow you to carry on working, you know, and sharing information with the organization. Jeff Bezos famously sent out an email saying, you're going to be totally autonomous. No team's allowed to be bigger than could be fed by 2 pizzas. All of your software is going to communicate by messaging. That's a boundary parameter. That says what they must do to fit into the vision for the organization. And so then they left the teams to get on with it and figure out how to solve the problems that were in front of them. The decision making was distributed. If you want to really scale this up, you also need to think about how to support those teams. You don't want every team solving every single problem individually, and that's really about identifying real common ideas, tactics, and common tools that are widely applicable and can be used by other teams. The key to getting this right is really to be able to abstract those ideas, have that loose coupling that we talked about earlier, to be able to build these platforms that many teams can depend on, but without depending on one particular version of that platform or another. That allows the teams to move forwards with the greatest degree of freedom. Some ideas, some techniques that can help you to kind of build this sort of autonomy. There's whiteboard models, sharing a vision, try and achieve within a team consensus, so that if you asked certainly any of the senior members of the team, but ideally any of the members of the team, you know, we need to solve this problem, they'd come up with very similar ideas of where in their design they would achieve that solution. You want some kind of shared picture of the design to achieve that. An accurate but vague working model of the system and a tool for exploring ideas, a kind of tourist map of the workings of the system. You consciously don't want it to be too detailed. This is one of my ideas. I call them whiteboard models, because one of the ways of managing the constraint on the detail is that anybody on the team, certainly any senior member of the team, should be able to reproduce your whiteboard model on a whiteboard with a pen without referring to any notes or anything else. So it's just what you can remember of the structure of the system. And that's the high level kind of, as I say, tourist map of the system. Avoid too much detail. Use the tool to introduce new team members to the system, to describe it, to tell stories about the system, and we want people to be able to recreate it from memory as a constraint on not getting into too much detail. Pair programming. Pair programming is, I think, an undervalued idea. Actually, pair everything. Getting people working together to achieve results is really valuable. The primary role of leaders is to teach, not to command. And pair programming is one of the best teaching tools that I know of. It allows us to free up the ability of a team to learn better than anything else. I'm not going to go into loads of detail about pair programming today, but I do have some videos on my YouTube channel that talk about pair programming and some of the other ideas here, including coupling and scaling up, that might be of interest. So the way to scale decision making and software development is by making it pervasive, distributed, and continuous, so that we can keep getting that valuable feedback, keep that learning underway, keep moving forwards all of the time. Thank you very much indeed for watching. I hope you've enjoyed my presentation, and I hope you found something valuable here. I will point you in the direction of my YouTube channel once more here. There's some more stuff that go into this kind of engineering thinking there that you might find interesting. Thanks very much, and I hope you enjoy the rest of the conference.
Thank you so much, David, for sharing your insight. I really appreciate the focus on the quality, because at the end of the day, that's actually what matters. It's not so much the infrastructure that we use to shipping our changes, but it's the experience that we deliver to our customers, their happiness and satisfaction. They all depend on the quality. So I just want to remind everyone who's watching that they are welcome to ask their questions in the Discord channel that is linked on the event page. So if you have any questions, please go there and ask them. In the meantime, I just wanted to hear your opinion on the connection between the continuous delivery and the production. So should there be a feedback loop, and how do you think it should look like to enable some of the past experimentation and other practices that you mentioned, so that we can actually capture the user sentiment and integrate it back into the development?
So I think that continuous delivery is nearly all about feedback loops, and that, as you've pointed out, that goes out into production as well. We want to gather feedback on the products and services that we are creating, so that we can learn from those. I usually break it up into two separate sections because I think you get different value from the technical practices of continuous delivery and what I refer to as continuous deployment, going into production frequently and regularly. So that continuous delivery is working so that your software is always in a releasable state. Even if you're in an organization or a business where it's not practical for you to release frequently into production, you can do it. It can allow you to do a better job at the technical level of, are we building the stuff right? Deploying frequently into production and gathering information, data, telemetry from our production systems and our customers' usage of our systems gives us a different kind of insight. If you're doing a good job of continuous delivery, they're not going to say an awful lot about the quality, because you'll have had that nailed in terms of the technical quality of what we're producing. But they're going to tell us about whether we're building the right things. So continuous delivery says, are we building things right? And continuous deployment says, are we building the right things? Is this idea one that lands with our users? Is this software stuff that really gives them value? Is it nice to use? Is it is it effective in amplifying their capabilities or whatever it is that you're trying to achieve? So I think gathering that information and feedback is a really important point, and taking kind of engineering thinking into production and allowing us to evolve better products is what the best companies do. The reason why Amazon and Google and Netflix and those sorts of places are doing well, and Tesla are doing well, is because they're releasing frequently, and so they can observe what works and what doesn't, and they can learn which ideas are landing with the users and not, and adapt. And I think that is absolutely that is probably the one idea, inspect and adapt, that's at the root of all of this stuff that I was talking about.
Awesome, thank you, David. And but you mentioned that there are so many practices for development, like pair programming or test-driven development. But I wonder if you have any techniques or practices that are specifically tailored for effectively capturing these like the customer sentiment, like maybe some sort of surveys, or I don't know, like A/B deployments, anything that you find most valuable for this kind of.
Yeah, I think there's a collection of things that you can do, and you've mentioned a few. So canary releasing, so you can release software into progressively more challenging environments to make sure that to get feedback on the quality and monitor its behavior, and you can do that fairly sophisticated. Use A/B testing to evaluate whether users like one version of the software version another, and you can take that quite seriously. And then there's just the regular kind of telemetry back from our system. So there's the technical stuff of is it working fast enough and all those sorts of things. But starting to measure the business impact, if you can identify what you hope the business impact is for one of your releases, and measure, is this gathering me more users? Am I getting more people signing up, new customers in, or are my users spending more money on my site, or whatever it might be as a result? And you can capture that data. That's going to be good too. I think again, the principle that we're talking about here across the board really is the scientific or engineering principle of working as a series of experiments. Our product changes to our products are experiments to see whether they're valuable to our users. Do our customers and our users value those changes? And we want to figure out whatever it takes to learn those lessons. So thinking carefully about how to gather that information and close the feedback loop is important. And for some systems that's easy. For others, I have a client who builds big scientific instruments, and they are deployed, on a customer's site with no link to the internet or connectivity where they can collect data. But we've been talking about them collecting key data points that they store. So if a service engineer goes out, they can just interrogate that information to see if it's if there is any useful data in terms of patterns of use or something that they can help their customers improve their use of the software as a result. So I think it's just understanding first that this stuff is valuable, and then in the context in which you're working, figuring out, so what are the experiments that I can take, and whatever the constraints, how do I get that information back in a way that I can learn from it?
So basically, truly, we have a situation where communication, collaboration of processes, and I guess.
Yes.
Yeah. Awesome. Well, thank you so much, David. I hope we're going to continue this conversation during the panel discussion. But at this point, we'll transition to the next talk, which is actually gonna be a natural continuation of our conversation of how to capture the production signal into the deployment pipeline and make sure that we actually are able to perform safe rollouts and other practices to capture customer sentiment. Thank you so much again, David, and we're going to see you at the panel.
Great, thank you.